Okay, welcome everybody. So today we're glad to have Sourav visiting us from Ashoka University to give a talk on proper affine actions of hyperbolic groups. Over to you.
Hi, everybody. I would like to thank the organizers for inviting me to give this talk. And even though it's part of the random geometry colloquium, but I don't think there'll be too much randomness or probability involved in my talk. I just hope that the general talk is not too random either. So I'll be talking about proper affine actions of hyperbolic groups. Essentially, you can think of non-abelian free groups in place of hyperbolic groups, and the full talk will go through essentially. So yeah, let's start. I don't think this is working. This thing is was working before. Oh. Oh yeah, this is working. Right. So the background of my talk. Oh, right. And another thing that I wanted to say is that there will be statements of results, like roughly formal statements, and then there'll be a heuristic given. So if you kind of feel lost, for students in the crowd, you can follow the heuristics. It will kind of be easier to follow those things. Right. So it starts with Bieberbach's theorems, where he classified groups, Euclidean crystallographic groups, so which are discrete subgroups of ON semi-direct product Rn, which act properly discontinuously and freely on Rn. And so he proved that they are virtually abelian. So essentially, up to a finite index subgroup, all of them kind of looks like n copies of Z direct product. So yeah, symmetry groups of compact tilings of Rn under Euclidean isometries are essentially n copies of Z. Later, Auslander and Margulis, they wondered if you change the group from ON semi-direct Rn to GL and R semi-direct Rn, and you ask the same question, can you have groups to start with not virtually abelian? Can you have other kinds of groups which act properly discontinuously and freely? And they figured out some examples. So one such example is here. So you take this upper triangular unipotent matrix A. I hope I didn't do anything. It's okay? Right. Should I go ahead or?
Go ahead.
Oh, okay. So yeah, so example is you take A, this upper triangular matrix, and then you take the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. And then you consider this group generated by AU, so this matrix, and in the translation component you have 0, 0, 1, that is U, and then identity matrix with this V 0, 1, 0, and identity matrix with W 1, 0, 0. So at the XY plane, it's essentially the Z2, but in the Z plane, the complicacy occur, and they observe that, oh my God, it's again not working, this thing. Maybe if you do that, then it starts working. No, if you, then I think it should start again. I think it starts again. Yeah. So I think every time you do an opening here. Yeah. Anyway, so observation is that, so this group that, the example that they found, it was polycyclic. So it's isomorphic to something like, oh my God. It's isomorphic to something like Z semi-direct Z cross Z. So because of this semi-direct product, it's polycyclic. And then later on, Auslander tried to prove this result that all affine crystallographic groups are of this form. But later on, I mean, it was figured out that there is a mistake in the proof, and the statement was rechristened as his conjecture, even though he didn't conjecture it in the beginning. Oh, the group. Yeah, so So the group is, you have A001. Right. Right. So I didn't check it. So as of now, I don't think I'll be able to move on. So Auslander, yeah, it's a three-dimensional matrix. So Auslander tried to prove this theorem, and he figured out, later on there was a mistake that was found in the proof. And then, so it essentially says that any symmetry group of tilings of Rn under affine transformations are semi-direct products of copies of Z. Now, this conjecture is still open, and it's only known to be true for dimensions less or equal 6 by results of Fried, Goldman, and Abel, Margulis, Schäfer. And the essential reason why the dimension is less than 6 is that they kind of list all possible Zariski closures of the group, and then individually they show that it's not possible in those Zariski closures. And in higher dimensions, this thing becomes more wild, and there's no general approach to this problem as yet. So later on, Milner sort of eased the case of cocompactness action. And so in case of Bieberbach theorem, one knows that if you remove the cocompactness assumption on the action, then again, it's essentially K copies of products of Z. And so Milner said that maybe it's better you look at the Auslander conjecture, but you do not assume cocompact action. And maybe still the conjecture will hold, or at least if it does not hold, it will be easier to find a counterexample in this case. So cocompact action is if you take a group which is acting on some space, in this case gamma acting on Rn, you would want Rn mod gamma to be compact, right? So heuristically speaking, that so you have symmetry groups of non-compact tilings of Rn under affine transformation. They're essentially semi-direct product of K copies of Z, isomorphic to semi-direct product of K copies of Z. Now, in 1984-83, Margulis came up with examples which showed that Milner's conjecture is false. Essentially, Milner didn't conjecture, he asked a question, and sort of also gave an approach how one could, if one would find a counterexample, how one could find it. And so Margulis' construction was kind of its existence construction, and he showed that so there exists Zariski dense non-abelian free subgroups of SO21 semi-direct R3, which act properly discontinuously and freely on R3. And later on, Abels, Margulis, Schäfer proved the statement that's written here, which is this dimension in R2n minus 1 case. So essentially, it says that symmetry groups of this affine proper actions, if you forget cocompactness, then it's free products of copies of Z and not semi-direct products. There are no relations at all. So for n equal to 2, it was done by Margulis, and later AMS did this SON n minus 1 version. And later in this talk, I'll state a result by Ilias Milga, which a recent result, which generalizes this construction to much more general semi-direct products of G, affine actions of G on Rns. So let's give a definition of what a Margulis spacetime is. So gamma be a finitely generated word hyperbolic group, and you take a representation of gamma inside SON n minus 1 semi-direct R2n minus 1. Let's say it's injective, and its linear part does not contain any parabolic elements. None of the examples that Margulis constructed had its linear part containing parabolic elements. But later on, examples were found by Drum where you could have linear part parabolic and still the affine action is proper, but we will not consider those things in this talk. And yeah, so rho is called a Margulis spacetime if this R2n minus 1 modulus rho gamma is a manifold, which means the action is properly discontinuous and free. And Drum also constructed fundamental domains of this kind of objects for Margulis. Yeah, by definition for us, there can be examples where you have proper action, which are non-hyperbolic groups. It's a result, recent result by Castle. So they show some coxeter groups acting properly discontinuously. But for this talk, we will only consider hyperbolic groups. So yeah, so he constructed fundamental domains in R3, and it's kind of, I'll try to give idea how these things are constructed. The essential idea is that the surprising part of Margulis's result was that you kind of roughly you think of free groups as things which have kind of exponential growth kind of a thing, and affine action, I don't know, somehow, at least to me, it feels like some kind of a linear or polynomial kind of an object. So it's a bit surprising that you could have this action, but then it's not surprising. I mean, it is an example by Margulis that you can. And what he's exploiting in that example is that in R3, you can, if you take the signature 2-1, then you can put the hyperboloid model of hyperbolic geometry, and you have free action there. And then, so you consider part of the free action, let's say, so these are the geodesics that you have on the hyperbolic plane, so the boundary of a domain, and then you consider the half tangent planes to those planes. So you have a hyperboloid sitting here, you take the planes which give you the lines on the hyperboloid, and you take the tangent plane to them to the light cone. And so from the proper action of the free group on the hyperboloid model, you will already get a kind of almost proper action on R3 itself. The only problematic point will be the center here, which will be a fixed point for this full action. So you have to kind of add translation parts, so part in R2n minus 1, and kind of make sure that you can separate this the knotted thing in between, and which directions are allowed, and that's essentially the construction by Drum here. And so I've shown you one particular example where you can separate out. So you can think of it from top. This visual is from the top, and this visual is from side here. So 4 such planes, and this bounds this region in between, which goes till infinity in these 4 ends, is a fundamental domain for such an action. Seen from aside, it's also like the part in between. So of course, like the other fundamental domains would be, so 3 will be coming here, 3 will be here, 3 other crooked planes will be here, 3 other crooked planes will be here, and so on, so forth. It will go till infinity in all the directions. Okay. It was not known during the time when Drum constructed these examples. He showed examples for some class of Margulis spacetimes, this kind of fundamental domains, and it was conjectured that any Margulis spacetime, 3-dimensional Margulis spacetime, will admit fundamental domains which are bounded by these crooked planes. So these kind of planes are called crooked planes. And this conjecture was solved recently, well, not so recently, 2014, by Danziger, Gerito, and Kassel, who showed that all 3-dimensional Margulis spacetimes admit fundamental domains bounded by crooked planes. So, so you start with the fundamental domain of a proper action of a free group of 2 generators on the upper half plane model, or like the hyperboloid model. And you take the planes which give you the geodesics on the upper half plane. So take this triangular part of that plane and take the tangent to the cone, half tangent to the cone, from the 2 sides of that triangle. So it does not matter, but I mean, but both should be similarly oriented. So I could have taken this on the other side, and this then would be this side. And certain like pluses will become minuses. Yeah. And it will be visible when I show the moduli space towards the end. And yeah, and then you take them, and if you take all such, they will be knotted at the origin. We'll have this kind of triangles and tangents passing out. And then when you separate them out from, so these are the places which were knotted before, seen from above. This one particular example I have shown that it has been separated, and so there's some checking here that it stays separated till infinity. And then this part in between, which is bounded by these crooked planes, is the fundamental domain of Margulis spacetime.
There's some assumption
Oh yeah, right. I should have added Zariskidens in SON in -1. Right, sure, that's correct. Yeah. So let's move on. So these things. So if you do not have any translation part, then all those elements fix the point 0. And then if you add the translation part, then the crooked planes, essentially the fundamental domain, gets a space in 0 and add some cocycle, right? Right. No, you cannot add arbit. So there'll be some open cone in. Oh, right. So that condition will come in precisely this slide. So it is observed that when a Margulis spacetime happens, it has these properties that the examples constructed by Margulis have this affine Anosov property, affine Anosov with respect to the stabilizer of a maximal isotropic affine subspace. So I'm not giving the definition of affine Anosov, but I will give you essentially what it means. So for something to be affine Anosov, it has to satisfy both these properties. So take individually any element of your group, consider its linear part. Because it's in SON n minus 1, it will surely have 1 as an eigenvalue. And then it will take hyperbolic elements, which are like loxodromic. And it will have this kind of matrix, block matrix A and A transpose inverse below when you sort of diagonalize it. And this 1 will be here. You would want, so there will be an eigenvalue gap here, or if you may prefer, singular value gap between 1 and here and 1 and here. And you want that to be increasing at the rate of the word length of gamma. So for bigger words, this gap should be much bigger. And also in the translation part, what you want is that the translation part of each of the element, when you break it down in terms of these eigenspace less than 1, eigenspace bigger than 1, and eigenspace equal to 1 decomposition, and take its component which comes in the eigenspace 1 part, that has to stay uniformly bounded away from 0. And it's essentially, we'll eventually see that this also is coming from some kind of Anosov property of the linear part itself, but as of now it's not visible. It's just similar kind of things where this is this stays separate uniformly from 1, and here it stays away from 0 uniformly. Kind of can be thought of derivative of log of this kind of objects, and we will see. We'll make this statement more precise. So yeah, and this property was used to, sorry, from right. And now we prove that this property is enough to guarantee proper affine action.
Yeah, but how we guarantee that there is an example of satisfying? I'm sure
right. So how would you guarantee? I mean, from Margulis and Ram's construction, except for that, this theorem is not guaranteeing you it will hold. It's only giving you a statement that if an action is proper, then this property should hold, and if this property holds, then the action should be proper. So it's an if and only if comment, and the proof really does not depend on existence. And yeah, so the statement is affine Anosov representations of a word hyperbolic group in SON n minus 1 simulate R2 n minus 1, act properly discontinuously and freely on R2n minus 1. So essentially, heuristically, it's saying that the examples of Margulis and other Margulis offer are essentially all of have affine Anosov property and vice versa. But here I must also say that the examples constructed by Drum, which had allowed linear parts having parabolic elements, those examples are not being taken care of here, because those examples will not have the linear part Anosov, whatever that means, will not have this uniform gap in their eigenvalues. And so we are not considering them in this talk. Most probably, I'm not sure. Check. So yeah, Satter's GLM proved this. Goldman, Laborie, Margulis proved this kind of a similar alternate statement for n equal to 2. And the general statement was proved by me and Nicholas Thribe in 2017. Let's see. Yeah. And this is not a very special thing. I mean, it's, well, it is a very special thing because of this very weird thing happening is that if you take SO n minus 1 and if you put it inside SO n, then the minimal parabolic subgroups of SO n cannot detect the middle eigenvalue gap. And I'll tell you what I mean. So, affine Anosov representations in SO n minus 1 semi-direct R2n minus 1 are infinitesimal versions of deformations of representations in SO n minus 1 inside SO n. So you start with a representation in SO n minus 1, and you put it inside SO n with a diagonal block like this. You start with something in SO n minus 1, you put it inside SO n with a diagonal 1, and then you deform the representation inside SO n. Right? So when you deform it, they will, because of the signature gap here, you will have eigenvalues lambda and lambda inverse surely. Now, you do not want this lambda to be ever equal to 1. But the minimal parabolic subgroup in SO n will not be able to detect this gap, because if you take the root system of SO n, it does not check the difference between this one and this one. And you have to check it inside SL2n or something else. So in my case, I'll take SL2n. And this is saying that if you start with a representation in SO n minus 1, which has this middle eigenvalue gap, and you put it inside SO n, and you deform it, only those deformations for which you have a uniform gap between this lambda and lambda inverse. That means they never become 1 and does not even come close to 1, stay bound, I mean, uniformly bounded away from 1, does not matter which element you're taking, how big the word element you're taking. If that property holds, then in those directions, if you take the derivative of the representations, those are the directions which give you affine Anosov representations, which means those are the directions which give you proper action. It's a very special thing that happens in SO n minus 1 inside SO n. It's not a, you cannot take any Lie group inside another. I mean, we'll see those examples also, but this is a very special behavior, not. So, yeah. So this was simultaneously and independently proved by me and Danziger Zhang in 2018. Right. Then, so using that the previous properties of this kind of uniform hyperbolicity, so you observe that if you have this uniform eigenvalue gaps between 1 and the rest of the elements, if you deform the representations a little bit, this gap still stays because of the uniformness. Yeah. Right. So if you consider the top eigenvalue and take its logarithm and you divide it by n or divide it by the word length of gamma, then this should stay away from 1. Right. 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 Guarantee. Yeah. So yeah. Right. So I'm just stating the condition of Anosovness using uniform eigenvalue gap condition, which is a result by Fanny Castle and Potri, and it uses results by Kapovich Lipurti and Guichard, Gerito, Castle Winhard, and also Andre Sambarino and some other people. I'm sorry, I'm forgetting a few names, but yeah, it's a lot of results that I'm using to guarantee that this jump from uniform eigenvalue gap and affine and Anosov representations linear part. Right. So using that affine that uniform gap property, you observe that when you deform, Anosov structure or this affine Anosov structure stays intact, and that gives us that it's an open set. That the modulus, if you consider the moduli space of Margulis spacetimes, then M is an open subset of the space of all representations, and it admits a natural fibration whose fibers are disjoint union of two convex cones. So this is where your original question comes. So these are up to a Z2 action. You have these two sides. So it's a fibration over the space. This kind of, in case of SL2R, you can think of this as a Teichmuller space, and on each point we'll have a fiber where the fibers look like this kind of open convex cone, and inside this region you have proper action, and outside you do not have proper action, and on the boundary things are a bit shaky. Yeah. And so yeah, this was proved by Goldman, Lowry, Margulis for three-dimensional Margulis spacetimes, and the general result was proved by me and Nicholas Tribe in 2017. Yes, till now in our talk, but eventually we'll see Smilga has constructed more examples, and yeah, which are general versions. But this is an interesting question. I don't think this is fully known, that whenever you have a proper action, does it have to end up in SON n-1 or some such thing, is something I don't know. Right. So so you use this formalism of the thermodynamical formalism to study the moduli space. Yeah. Yeah. No. So what I'm taking is that you take representation rho from gamma inside SON n-1 symmetric R2 n-1, and you see up to conjugacy. Yeah.
That will have where when you push it out by conjugation,
right.
You're saying there's some statement here that the Anosov does not take that.
Correct. So Anosov, from other results, it's guaranteed that you do not have those kind of bad points when you have Anosov, and because it gives you, essentially because of this uniform eigenvalue gap property, and from there those things do not create any problem in our case. So we do not have to care about the intricacies of GIT quotients. And on the moduli space, using this thermodynamical formalism, we try to study the geometry of the moduli space. And so this is the study of entropy, pressure, which should be called free energy, but somehow it's called pressure in the literature, and intersection number of Holder continuous functions. It's kind of, it checks essentially what's the growth rate of like those kind of the lengths of closed curves of a given length, and how many there are when you increase that length. And so you sorry, what did just happen? I have no clue. Could you? My PDF is supposed to have a, yeah. I think it's coming after this. The slides are there, right? Slides are there, right? Yeah. Yeah, this one. Right, so let's. Right, so correct. Right. Right, yeah. Yes, right. So so this kind of objects give you a kind of, we get freely a non-negative quadratic form called the pressure form on the space of pressure zero Holder continuous functions. So this we get as a package from thermodynamic formalism, which was developed by Abramov, Bowen, Ruel, Perry-Policott, Macmullen, Sarig between 1950 and 2023, and I think Bowen was instrumental in it. At least I learned a lot from reading his book. Right. So using that, we get this pressure form on our moduli space because we show that. I think there's one book, Abramov or someone had some entropy or something. No, sure, but I consider the definition of entropy to be also. So, right. So M admits a natural embedding into the space of pressure zero Holder continuous functions. And this is essentially, if you take the continuous versions of the length data, like it's some function which when integrated over loops corresponding to gamma gives you the corresponding lengths in your system. It's kind of that function. So that gives an embedding of M into the space of pressure zero Holder continuous function. There's something to be checked. Along the closed geodesics, right, which gives you the length of your representation, quote unquote length of your representation. Right, yeah. And so using those functions, you can embed M inside this space of pressure zero functions. And so you get the pressure form, and then you have to check certain things. It's a finite dimensional moduli space, right? Oh, no, wait. Oh, right. No. So similar statements will come later, and yeah, which will answer your question. So, so we show that this form has signature, like it's not fully Riemannian. It has n-1 Riemannian part and a zero part, which just doesn't see anything at all. And so we remember the fiber product. So in the fibers, you had this open convex cones. So the lines which goes to infinity, in those directions, the pressure norm, pressure form gives you zero norm. And on these kind of directions, which are, so if you take constant entropy sections of your moduli space, on that constant entropy sections, you have the restriction of the pressure form gives you a Riemannian metric. And the three-dimensional case was done in 2015 and the general in 2019. But this form, I should also say that this is very difficult to compute because of this thermodynamical formalism quantities coming in picture. It's very difficult to compute geodesics for this Riemannian metric. And also, what would the geodesic mean geometrically? It's an ongoing project, but I don't think too much has been done. Right. Right. You get well, Peter. And right. So this is the thing that I was saying, the generalization that Smilga did. So he showed that if you take any non-compact semi-simple Lie group, it has to be essential, non-compact, otherwise you cannot have proper action. And take any representation of G inside GLN, irreducible representation, which admits 0 as a weight, which means that you guarantee 1 as an eigenvalue. It has to be there. Those are the directions in which kind of the translations will have space to move. And also there is this condition that the longest element of the Weil group should act non-trivially on the 0 weights. Then there are non-abelian free groups inside this G semi-direct product Rn acting via this representation R, which acts properly discontinuously Rn with Zariski-Renz linear part. So I forgot to add the Zariski-Renz condition in the beginning, but now, yeah. So heuristically, roughly what this is saying is that for this representation, identity minus Rg for any element G should have determinant 0, surely. And the eigenvalues of modulus less than 1 of Rg and Rg inverse should be equal. So I'm saying roughly because, I'm not truly giving the full idea of this case that the longest element act non-trivially. What is written here is essentially saying that the longest element act by a negative sign. But it's more generally this statement is true. This result was done for the adjoint representation case in 2014 by Smilga and the general case in 2016. So we have more examples of proper affine action, and we call these Margulis Smilga spaces. So you take any reducible representation which admit this thing. So it's not any reducible representation, but which satisfy this. Oh, okay. Because in case of the adjoint representation, you have the longest element of the Weil group exactly doing minus of that thing, and so it is non-trivial, and that is the heuristic that I have written here. This is the adjoint representation heuristic, not the general thing. Right. So for these spaces, under some more assumption, I prove. It starts with Drum Goldman in 2001. Then there was a result by Kim, which is I find the proof a little bit not so sure, and it was then generalized in 2020 by me. So we prove that if let's say gamma is a Ward hyperbolic group and G be a split Lie group, and we also have a condition on the representation R which satisfy R is conjugate to R transpose inverse. So this condition essentially guarantees some kind of a norm on your space which stays invariant under the group. Yeah, real split. Yeah, we are always working with real Lie groups. And you take two representations inside G semi-direct Rn. Let's say these two B are Margulis-Smilga spaces whose marked length spectrum. I didn't introduce what this length is. So previously we saw that projection of the translation part onto the unit eigenspace had something to do. Here also we'll take the projection of those elements onto unit eigenspaces. But now because the unit eigenspace have more than one dimension, so the objects that we'll get in place of length will not be real numbers, but they'll be vector valued objects. And if those match up you always have this marking. So for two representations of this kind, which give you Margulis-Smilga spaces, then they are up to conjugacy, they are the same. So heuristically, this is saying that the mark length spectrum fully determines the Margulis-Smilga space up to conjugacy. So this was done inspired by rigidity results of Mosto, Prasad, and Margulis the case SO21 was done by Drum Goldman in 2001. And in the case 2n minus 1 was done by Kim in 2005, and the general one in 2020 by me. In fact, as you asked before, that there should be, because it's a finite dimensional space, you should be able to detect it using finitely many. So this is another result that I proved recently, that actually you do not need to use the full the spectrum to be same, but given a generating set and given this group, so you fix G semi-direct Rn, and you consider two representations, then I can give you, so formally, so let gamma G R be as in the previous slide, and you take two representations inside G semi-direct Rn, be two Margulis-Smilga spaces, whose marked length spectrum are equal up to wards of length at most k, and this k depends on the generating set which has been fixed from before, and only on G semi-direct Rn. That means it does not depend on the representations at all. Then there exists an automorphism of the bigger group which conjugates one to the other. No, what I'm saying is that if you take bigger generating sets, then you might need this k. You might not need too many. So from that angle, yeah. So heuristically, this means that checking only finitely many suffices, and it essentially uses in a very essential way. So this lemma, which is called escape from subvarieties lemma by Eskin Moses O, kind of uses some algebraic geometric techniques. You try to show that your object is inside some algebraic variety, and then to determine an algebraic variety, only finitely many points are needed. Essentially, this kind of an argument is used to prove this. Now, we'll define what is called a Hitchin representation, and we'll try to relate what this has to do in our case. So, so let gamma inside SL2 be a Fuchsian group, that is a fundamental group of a closed compact surface without boundary. Free groups come as fundamental groups of closed compact surface with boundary, right? And then you call a representation inside SLN a Fuchsian representation if it comes via a irreducible representation of SL2 inside SLN. So you take a group inside SL2 and you consider the irreducible representation of SL2 inside SLN and put the group gamma inside SLN via such a thing. You call such representations Fuchsian representations. And what Hitchin proved in 1992 that connected components of representation variety which contain these Fuchsian representations, they are topologically trivial, which means they're homomorphic to open balls. And these the representations in these connected components are called Hitchin representations. In fact, all this theory of Anosov and thing started, this uniform eigenvalue gap started from Hitchin representations, trying to study Hitchin representations. So Laburi was trying to find properties of representations inside the Hitchin component, and he figured out that if you take any representation inside the Hitchin component, they always have so all the eigenvalues have uniform gaps between them. So for Fuchsian representations, this is kind of visible because in SL2 you have this lambda inverse, and when you put it inside SLN via this kind of irreducible representation, the eigenvalues become lambda to the n minus 1, blah 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 1, and the other way around. And this uniform gap still stays. And he also used another criterion to characterize it. This is not enough to characterize any representation inside the Hitchin component. So he also said something about the limit curve, which has to be decent. Yeah. So yeah, any representation rho of gamma inside SLN which lie in the same connected components containing the Fuchsian representation are called Hitchin representations. Now, so there is this non-existence result. So first, let's try to see that when you have a free group acting, the example that we saw from Ram's construction, that when the free group acts on the upper half plane model, you had this kind of openings, which kind of helped roughly, which kind of helped finding these translation directions where you can move the crooked planes to get a fundamental domain. So if you start with a group which is a surface group whose limit curve is a full thing, then you will not find any direction in which you can disentangle all those crooked planes. But this is of course not a proof. So Mace in 1990, using some other techniques, he proved that there does not exist any row representation in SL2 semi-direct over Lie algebra SL2, and this representation is the adjoint representation, which act properly discontinuously on Lie algebra SL2, and which has Fuchsian linear part. And this was later proved by Goldman Margulis in 2000 also. And the essential idea of the proof is that I think due to a result by Thurston, you cannot have, if you deform the surfaces, you cannot have all the lengths going up in any direction. So there'll be some length which goes down, and they essentially give a so they interpret this length of the affine part as derivative of these eigenvalues. So having decreasing eigenvalue or decreasing length on surfaces would mean that you have a direction which is opposite. I mean, which is not, it will not satisfy the affine Anosov property that we saw, and because of that, this will not hold. So observation is that the adjoint action of SL2 on its Lie algebra is essentially the same as the linear action of SO21 on R3. I mean, I say essentially the same because in SL2 you have something more. So actually it should be, if you had written PSL2, then it will essentially be this SO21. It's the same kind of action. So this is kind of stating that Margulis's example is not possible if you do not take free groups, and if you take surface groups, fundamental groups of surfaces with no boundary. Recently, by Labouri, it was proved that, in fact, if you take Fuchsian representations inside SLN or SON in -1, so there does not exist any such representation of gamma, where gamma is a surface group inside SON in -1 semi-direct R2n -1, which act properly discontinuously on R2n -1, and which has Fuchsian/Hitchin linear part. The Fuchsian thing was done by Labouri in 2001, and the Hitchin part was done by Danziger Zhang, and later Labouri in 2018. And they show that this is not possible. So I will kind of, so starting from this kind of an observation, one could kind of conjecture that you can start, so let's say you can start with the Fuchsian linear part and consider representations rho inside SLN semi-direct, the Lie algebra SLN. So I want to know there does not exist any such representations which act properly discontinuously on the Lie algebra part and which has Fuchsian linear part. Well, I've written it as a conjecture essentially because we kind of know the answer to it, or it's work in progress by several. Oh, so here Fuchsian would mean that you take the representation rho, I take a Fuchsian group inside SL2R, and you put it inside SLNR via irreducible representation, right? And then for that you want to see if that can come up as a linear part of for the adjoint representation on SLN for a proper affine action. And yeah, so this is some work going on, and soon something should be on arXiv sooner or later. And yeah, thank you. Sorry. Okay.
So you can't just think about then
Right.
there is something that 9 E minus none real lengths.
Right.
Determined for the.
Right.
Given the two positive and all the. What are
So in right, so I so the egg,
constructing separate pressure zero.
right. So there exactly which ones are needed, I will not be able to tell you, but from this result from 2021, I'll
About T growth, right? But that should really be determined by A, the group itself.
Right.
And the group into which you are. It's not have any other effect. So maybe.
right. So the result. Right. So in this case, so in the case when you have adjoint representation, I think one would be able to say more stuff. So in case of SL2 or semi-direct, the Lie algebra SL2, in that case, because we know this fact that the affine translations come from derivatives of the eigenvalues, we can say more. But because in the general, in the SON n minus 1 case, those are coming from representations inside SONN, and the deformations do not give you Hitchin representations. That's some result. So if you start with Hitchin representation inside SONN minus 1 and you deform it inside SONN, it does not stay Hitchin anymore. And because of that, this kind of control is gone. I mean, and we do not have like to be able to say exactly which functions will determine it. Yeah. So it's not too explicit. So there is so we can compute that K, some upper bound, but except for that, not too much.
What properties do those functions have besides?
No, it's not chosen that way. It's chosen in an the proof goes something like you try to put your space inside some algebraic variety, and then it's kind of an existence result that if you start from the center and you increase the number of elements, then after a finite point, it should determine the algebraic variety fully, and you don't need to check anymore.
So it's some kind of heuristic and skills are, I mean,
I don't know what this kind of arguments are called colloquially, but this argument appeared in this Eskin Moses O paper called the escape from subvarieties lemma, and they use it to show kind of an some other result. Yeah. Right. Right. This one. Right. Right. So. So it will be point is it will be some restricted kind of those spaces, the kind of lengths that you would get after integrating over the closed curves, they'll have some more restrictions. So starting, you can think of this pressure zero Holder continuous space of Holder continuous functions pressure zero as all kind of maybe more than all possible representations, because you can consider any anosov representation and take this length thing, and that will again give you a pressure zero Holder continuous function due to results of Bridgeburn, Canary, Laburi, Samborino. So it's kind of a so this space contains much more than we have, and so I don't think that they're just starting from the space of pressure zero Holder continuous functions. If you try to ask which one of them will give you Margulis spacetimes, one tongue-in-cheek answer will be you check the spectrum and maybe try it with some Margulis spacetime if it matches or not, or some such thing. But and try only for this finitely many because of this finite result. But except for that, I don't think I can say much more. Yeah.
there are no further questions. Thanks. Okay.